Alright, welcome to our third lesson about limits. This is evaluating limits and limits at infinity. So when you're asked about limits at infinity, I've got a lot of information here, but notice the limit notation here is asking about limits at as x approaches negative infinity or positive infinity. So they'll always be set up like this. However, the equation is going to be pretty specific to a certain type of function. So here we're looking at polynomials, and you might recognize this table from previous pre-cal or algebra 2 classes. This is the way end behavior functions for a polynomial. So if I've got y equals x squared, then that's an even degree polynomial with a positive leading coefficient, so its ends will be pointed up. Likewise, if you wanted to see some examples of odd degree polynomials that start by pointing down to the right and go up and to the left, then that's a negative leading coefficient and an odd degree. So you've definitely seen this table before. I just wanted to remind you of it. The limits that we will be evaluating, like number 1 here, have somewhat of a strange form. If we're using this table, we need to know what the leading term is. And I know that my leading term, if I multiply this out some, my leading term is going to be 6x squared plus is just going to be x squared. I can multiply the rest of it out just for funsies, but I really only care about x squared because that's going to determine the end behavior of this entire polynomial. And in turn, the end behavior is going to directly relate to the limit itself. So the limit as x approaches infinity on this quadratic is infinity. So it's the right half of the quadratic that is pointing up towards the y values positive infinity. And if we ask that same question of number 2, as we approach positive infinity with our x values, our y values go down because we're actually looking at this type of graph. So my y values go to negative infinity. So really all you're doing is you're answering an end behavior question. Here my leading term, by the way, you know that 3/2 x to the 7th is the leading term because it has the highest degree, the degree being 7. And this is an odd degree polynomial, and we are going towards negative infinity. So my polynomial, I know there are more curves in it than that, but I know that the right side in behavior is going to go towards positive infinity in y, and the left side in behavior is going to go towards negative infinity in y. So what's happening as x approaches negative infinity? That's going towards the y values that are approaching negative infinity. So I'm just making sure I'm following the end behavior. And I do have a lot of tables here for us to look at. If you cannot remember these tables, we can substitute in very large positive or negative numbers. And I'll show you what I mean when we get into these examples here. So for this table, we're given a look at radicals, a little reminder about how radicals work. If b is an odd number, an example could be x over x to the 1/3. Then a sketch of x to the 1/3 or any odd radical, odd degree radical, is going to look something like this. If b is even, then your radical will only have one positive piece. And that has to do with how the domain works on these radicals. But if we're discussing in behavior, then we can reference this graph. We can also think about as x approaches infinity, y will approach infinity, and then when it goes to negative infinity, y will approach negative infinity. And when we are looking at a radical when b is even, as x approaches infinity, y will approach infinity, but as x approaches negative infinity, there's no limit to look at. So this is d and e. The limit does not exist. Square root x there. All right, and then we'll go through these examples first. So if we look at the end behavior on x to the 1/2, this is just radical x. So the limit as x approaches infinity is going to be infinity. Radical x grows very slowly, but it does get closer to the y values infinity. Now, based on how we were looking at limits in the first place, we had to look at the left and right side of these things, of these limits, of the value in question. So if I were to write something like infinity to the right, that doesn't make any sense. There's not a right side to infinity. That would just be infinity. So there's no such thing as a right or left-hand limit with infinite limits. So we're just looking at what is the end behavior, where is this graph trending? For number 2, we're going to be looking at negative infinity. I've already answered this question actually. This is d and e, because this is a radical, again radical x, and we don't have anywhere to go on radical x as we approach negative infinity. There's no shape to follow, so we can't approach anything. Now here we have a odd degree radical because it's 1/5, and I want to know what's happening as x goes to negative infinity, and that's negative infinity, just based on the pattern that we have up here. It'll always be true. So 2 and 3 were easy enough, but 4 and 5 have multiple terms in their polynomial. So while we've learned some new information about radicals, which we do have some radical degrees here, we need to respect the largest degree still. So we have to respect the largest degree in our polynomial. Because this term, negative 4x to the 4th and 4x cubed, they are the leading, they have the leading coefficient because it matches the largest degree. So these are actually not radical problems, they are polynomial problems where we follow the polynomial end behavior. So this is a negative, even, power polynomial, so I can draw the ends of it, and if we're going towards negative infinity in x, then we're going towards negative infinity in y. And for number 5, if I'm going towards negative infinity in x, this polynomial is cubic mostly, then we are headed towards negative infinity and y. So be careful to check to see if there's a higher degree than what is at the beginning of the polynomial. Don't always assume that the beginning of the polynomial has the largest degree. Cool. So let's look at how exponential functions work. If we take this equation, f of x equals a to the x, and we sketch a little thumbnail, that will produce a decay exponential graph. A growth type graph would happen if a is greater than 1. So our end behavior, as x approaches infinity for our decay, y will actually approach 0. As x approaches negative infinity, then y will approach positive infinity. And then you can kind of see where this is going. As x approaches infinity, y will approach infinity. If we understand that it's a growth type exponential equation, and as x approaches negative infinity, y will approach 0. And that's because we have horizontal asymptotes on these exponential equations. So we're going to look at some more examples of all the types now. For number 6, we are checking the largest degree, and it's saying that our graph is built like so. And as we approach negative infinity, then our cubic is forcing our entire graph, our cubic power is forcing our entire graph to go to negative infinity. Our y values are going to approach negative infinity. In number 7, that's an exponential equation, this 2 to the x. So it's a growth because a is greater than 1, so this is infinity. Number 8 has a kind of complex degree, but we can see that if we plugged in a really, really large x value into our numerator, this thing would continue to grow into our, not numerator, but into our exponent, then this would continue to grow. So this is also infinity. And then as we make our exponent more negative, remember negative exponents make a fraction out of that value. So this approaches a very, very, very small fraction, but a positive fraction nonetheless, so this approaches 0. And again, the reason I'm showing you this is so you don't have to type everything into a calculator, scale it, look at it. You have a little bit more of a way to test that. Again, if you really want to just sketch out some numbers, like what happens if we start at, I don't know, negative 10. Then this is 1 over 2 to the 20th. So that's a large number in the denominator, but it's going to be basically 0 if we keep on going with it. So that means our limit is 0 because we approach 0. And then with 10, we have, in 10 and 11, we have a values that are between 0 and 1. So these are decay. So as we approach infinity on a decay graph, we approach 0. As we approach negative infinity, our y values skyrocket to infinity. Alright, so there you have it. You'll be practicing some of this, and I'll talk to you all later. Bye.